When the night has come and the land is dark and the moon is the only light we'll see.
In this problem, we're given the Maclaurin series for e to the x, and it's given as 1 plus x squared over 2 plus x cubed over 6, and then the general term is x to the n over n factorial. It says the continuous function f is defined by, and you have f is, in the numerator you have e to the x minus 1 quantity squared minus 1 all over x minus 1 squared. And that specifies for x not equal to 1. You're also given that f of 1 is equal to 1. The function f has derivatives of all orders at x equals 1. Part A says write the first 4 non-zero terms and the general term of the Taylor series for e to the quantity x minus 1 squared about x equals 1. So we're given e to the x, it's written out right here. We want to find e to the quantity x minus 1 squared. So instead of x, we have x minus 1 squared. So I've plugged in x minus 1 squared anywhere there was an x in the original problem. And then when you simplify, you have powers to powers. So you multiply those exponents to get 4 here. You multiply these to get the 6. So your exponent on the general term is the 2n. Remember, if you plug in 0 to this, you will get an initial term of 1. When you plug in 1, you get x minus 1 squared. When you plug in 2, you get x minus 1 to the 4th, and so on. So that gives you your numerator of your general term. In the denominator, you still have, in the denominator technically right here would be 0 factorial, this is 1 factorial, this is 2 factorial, this is 3 factorial. So it ends up that your denominator is going to be n factorial for that general term. So here's your whole expression for e to the x minus 1 squared. Part B says use the Taylor series found in Part A to write the first 4 non-zero terms and the general term of the Taylor series for f about x equals 1. So I wrote out f again. You have e to the x minus 1 squared minus 1 all over x minus 1 squared. So it looks kind of intense, but we're taking this entire series and we're plugging it in right here, and you have this whole series. You still have minus 1 all over the quantity x minus 1 squared. So the 1's canceled, and now you have all of these expressions that you're dividing out, this x minus 1 squared. Okay, so this first term divided by this gives you the 1. These guys made quantity squared over 2. These reduced and made quantity to the 4th over 6. The next term up here would have been x minus 1 to the 8th over x minus 1 squared would leave you with x minus 1 to the 6th. In the denominator, remember you're following the pattern of 2 factorial, 3 factorial, so that's why this is 4 factorial or 24. And then you have your general term. Remember, all these powers are still evens, so you're still writing x minus 1 to the 2n. In the bottom, you have 1 factorial, 2 factorial, 3 factorial, and 4 factorial. But up here, in the powers, this is 2 times 1, this is 2 times 2, 2 times 3. So the n is 3, but this is 4 factorial. So that's why you have n right here, but this is n plus 1 factorial. So here's your expression for f. Part C says use the ratio test to find the interval of convergence for the Taylor series found in Part B. To set up the ratio test, you have the limit as n goes to infinity, absolute value. This is a sub n plus 1. So I took this general term from Part B. Anywhere I saw an n, I plugged in n plus 1. And then you divide by a sub n, which is the same as multiplying by its reciprocal. So you get x minus 1 to the 2n plus 2. Down here you have n plus 2 factorial, and then these stayed the same. Now we're going to simplify. We're going to split this up to x minus 1 to the 2n times x minus 1 to the 2. The x minus 1 to the 2n's will cancel here. So I took the n plus 2 factorial and rewrote it as n plus 2 times n plus 1 factorial. So now this n plus 1 factorial and this n plus 1 factorial will cancel. Next, we can take this expression with x and pull it to the front, and then you just have the limit as n goes to infinity of 1 over n plus 2. As n gets larger and larger, this fraction is going to go to 0. Since this goes to 0, your whole expression ends up being 0. 0 is always less than 1 for all numbers. Therefore, the interval of convergence is going to be negative infinity to positive infinity. Part D says use the Taylor series for f about x equals 1 to determine whether the graph of f has any points of inflection. So we're using the formula for f, 1 plus x minus 1 squared over 2 plus x minus 1 to the 4th over 6, and so on. And we're going to take the derivative of each of these terms to get f prime. Now we're going to take the second derivative. The derivative of x is 1. The derivative of -1 is 0. Here we're going to bring the 3 to the front. The 3's cancel, and then subtract 1 from the exponent. And then finally here you get 5/4 x minus 1 to the 4th. Since all of these powers are even, whatever value you plug in for x, you're always going to get out a positive value. Therefore, we can conclude that f double prime of x is going to be greater or equal to 0 for all x. Since there's no sign change on the second derivative of f, that means f has no points of inflection.
So darling, darling, stand by me. Won't you stand by me? Just as long as you stand by me.